Welcome back, everyone, to the fundamentals of mechanical design. Today we're talking about principal stresses and how important they really are, and how really what they're getting at is that every stress caused by every force can be looked at as a combination of normal and shear stress. Let's check it out. So the first thing to understand about principal stress is that really what it's getting at is that everything is normal and shear. It just depends on how you look at it. So let's first of all consider the simplest possible case of looking at stress. That's normal one-dimensional stress, where we have a force over an area that's applied either in tension, that's pulling, or in compression, that's pushing. So really what normal stress is saying is it's got a perpendicularity from the area to the force, 90 degrees. And so let's use a couple symbols here for pulling and for pushing. Moving on to shear stress. Well, how can we visualize this the easiest possible way? In my opinion, it's with a direct shear setup, where two pieces of, let's say, wood or metal are connected with a pin. And if you pull on those two pieces of wood or metal, you're actually trying to shear the pin. Pin looks a lot like the normal stress bar and tension above, doesn't it? That's exactly why we get the same equation. Instead of 1D, now we're looking in 2D. Instead of perpendicular, now we're looking at parallel. This is the key. Let's throw a symbol on this, keep rolling. Okay, so now we're going to take it to the next level, and we're going to say that we can actually have normal and shear in the same piece, even the one we started with, depending on how we look at it. How does this work? Well, let's look at two teeny chunks inside. The yellow one, pretty straightforward, perpendicular to the force, just like we've had all along. We're just going to see that that one is in pure tension, seeing normal stress. But does the blue one also have shear just because it's angled? Well, let's cut the bar and sort of analyze these orange faces as kind of similar. And let's also recall some vector mathematics, and let's recall equal and opposite from Newton's third law. Inside forces, perpendicular and parallel, add up to outside force applied. So at what angle the minimum and maximum normal and shear stresses occur is really important to think about here. Obviously, maximum normal stress occurs at 0 degrees, but what about shear? This is the interesting question, and we have to do a little bit of math to think it through. So let's label a few more things on our drawing here, including the original sort of area we looked at as A0, and this new area, this cut area, as A theta. So that means just sort of the angled A. And, recall a little bit of classic trig. We can actually get a relation between these two. Recall the equations we learned above. We're just going to label a few more things here. Recall some vector mathematics. And then we're going to put all this together to just look at the shear stress. And when we put it together, we realize, wow, this is just force over area with this additional term, sine theta, cosine theta. When's that max? It's max at 45 degrees. So this is so interesting. We're seeing normal and shear everywhere. Where else do we see it? We also see it when we're doing bending of beams. Classic pure bending, what is it? Well, it's nothing but tension on the top and compression on the bottom. Nothing but normal stress on the top and the bottom, pulling and pushing, nothing but normal. We also have shear stress in beams. And the shear stress can be thought of as directly analogous to our direct shear. We're going to try to sort of picture it here, maybe flip it up on its side a little bit, and kind of try to draw the parallel a little more directly to the direct shear. Okay? Lastly, think about torsion. Won't take you very long. Think about the pin. Same deal. Okay, so here we are. What's a principal stress then? Well, principal stress is just the maximum normal stress. That's it. Because we have XYZ that we're often looking at things, but really, if we're oriented in some other direction, we might go 1, 2, 3. And if we have a special geometry like, say, a cylinder, we might call it longitudinal and tangential and radial. Now, after we look at normal, we also need to look at maximum shear. Once we look at normal and shear, what have we got? We've got our general three-dimensional stress state. From any general 3D stress state, we can get a single stress with which to design. That's going to allow us to pick our strength. That's going to allow us to pick our material. That's going to allow us to design our design within some factor of safety. And that's all there is to it.